Hello everyone, welcome to this video. Today we are going to solve this integral. So this is a double integral involving trigonometric functions and algebraic functions. So yes, this is a very difficult integral, and this is one of the type of the integrals that had actually I wanted to give this type of integrals only on this channel, but I have given a lot of this stuff. But this would be the main focus because this is my area of interest. Usually the problems which are, very difficult and it takes multiple steps and multiple concepts to do them. And we will see why exactly. I'm not exaggerating at all. This is indeed a hard integral and there will be more of this on the way. So, okay. So this is a double integral first of all. So will not really focus on the concepts that are required to do double integration, specifically like order of integration and stuff. So this problem would not deal with much of that, but I will give away bits and pieces of information whenever required. So to start off, this type of an integral cannot be dealt like simply by substituting stuff and as we do in that normally in one variable integration, like we try to find something that is in the numerator or denominator. So none of that stuff sort works. Basically you can try it out on your own. So the first thing we are going to do is we are going to define a function with the parameter a, which looks something like this. So put the double integrals like this, and then sine x sine y divided by xy into x plus y, and multiply this with e to the power minus of a whole into x plus y, and then put dx and dy and define this function for all a greater than 0 where a is a real number. What is the motivation behind this sudden change of, sudden parameterization? This is called a Feynman parameterization. You can see the card above. So that also shows an integral of this type. Not really this hard, but yeah, we'll get the idea from that integral. After you watch this one, you can go ahead and watch that one in order to get a clear idea. Okay, so the motivation is basically to differentiate function with respect to a, so that the coefficient when we differentiate with respect to a, we get x plus y in the numerator. Because when you differentiate e to the power minus x, let's say, and there is a constant ax, what we get is a into e to the power ax, right? But we are basically doing it with respect to a, and since we are doing it partially with respect to a, the answer here, the coefficient would be x plus y into minus 1, right? So minus of x plus y would be the coefficient, and that would be in the numerator. And what happens is when it comes in the numerator, we can basically cancel it off. So let's go ahead and do that. So differentiate it under the integral sign. And first of all, the integral is convergent, and so is this integral for any a greater than 0. You're free to verify that. And all the rules of differentiation and integration hold here. It usually does hold in almost all cases wherever the integral is convergent, but there are exceptions, of course. But in this case, it does hold. There are no issues. So 0 to infinity, put a minus sign because we are going to get it. We have sine x, sine of y divided by xy multiplied by, we will get our usual e to the power minus x plus y here, but we will also get an x plus y, right? Which will cancel with the corresponding x plus y like this. And now we have this integral. Now this integral is in variable separable form. You might have heard that term in differential equations, but it is also something that will help us in integrals as well, where there are more than one integrals involved, like iterated integrals, right? So you can see that this can be written as sin x by x multiplied by e to the power minus ax dx. And okay, let's just first do this step and then separate it. And also sin y by y e to the power minus ay dy. And now, since there is no mixed term here, so you can see clearly there is no term which involves both x and y. So the x integral is completely separate from the y integral. We can simply write this as a product of two integrals. And yes, this is an valid operation. You can apply it in other sums as well, whenever possible. So if you can get variable separable integrals inside of a double integral or a triple integral, you can do that. You can always do that. Okay. So this is again this minus ay dy. Okay, we are done. We're good. Now, Since you can understand that definite integration simply refers to a certain area under a curve, the variable does not matter. So what you see here is exactly what you see here. So it does not matter if I use a z or a w or a p for the variable here or here. And you can see they're identical integrals. So basically, this second integral is simply equal to the first integral. It's a copy of the first integral just in terms of y. So what we can do is we can write this integral as a whole square now because there are two of this, right? So sine x upon x e to the power minus ax dx, and then you can do a whole square. Okay, great. So this is our f prime a, which is the derivative of f at the point a, where a is a parameter as we have defined for a greater than 0. Correct? Now let's define this function as g of a because this is also dependent on a, and let's do that simply. So you will again see a video on the top right, which basically where I have basically done this in order to find out the integral of sin x upon x. And that was a simpler version of this one. This time we are not going to find out sin x upon x, rather the whole integral. Okay. So we basically follow the same procedure. We differentiate again GA because we do not really want this x in the denominator, right? So minus 0 to infinity, as you can understand, minus x would have come out as a coefficient. It would be e to the power minus ax sin x dx. And in the video that you have seen in the cards above on the top right, this has been evaluated. You simply have to take sin x as an imaginary part of e to the power ix, and then you can evaluate this integral, which should come out as this 1 plus a square. Okay. Okay. Now from GA, we will deduce a few things. First of all, g of 0 is simply the integral 0 to infinity. G of 0, let's say it is defined at, obviously, this function is defined at a equals to 0. So we can let that happen. Similarly, actually have to make this a greater than equal to 0 because at a equals to 0, of course, the integral is defined. So a greater than equal to 0. Okay, g of 0 basically is the integral sin x upon x dx. And this integral is already done. You can see the video, which is pi by 2. And if you let a tends to infinity for g of a, this term goes to 0. And this is a convergent integral, and we can basically interchange the limit and integral here. And due to which this basically becomes 0 as well. Okay, so from this, what we do infer is this: we want to find out the limits of integration when we are trying to find out GA from G dash. So when there is a, let's write down this first. This is a better procedure with respect to dA, of course. And then we have minus dA upon 1 plus a square. We're integrating both sides. So when there is infinity here, there is 0 here, right? And when there is 0 here, like this, since this is 0, so you can understand what's basically going on here. So infinity 0 and 0 to infinity would give you the answer. So actually we need to do it up to a, I guess, right? So yeah, let's do it up to a. That would be a better option actually, because we do not really need the value of g0 rather, because we already know it. So we will need something else. Okay, let's do from 0 to a actually. That's better because we should get GA. So due to fundamental theorem of integral calculus, this should be GA minus G0, right? And this has an antiderivative of arc tan A or tan inverse A, which should be then tan inverse of A minus 0, because tan inverse 0 is 0. Therefore, G of A simply becomes G of 0 minus tan inverse of A, correct? And due to this, since G of 0 is pi by 2, as I told you before, this becomes pi by 2 minus tan inverse A, which is simply cot inverse A. Correct. So that is the value of G of A. So this integral here is basically cot inverse A. Therefore, what we do get from that is f dash t is nothing but minus of cot inverse A whole square. Now, again, come back to the definition of f of a, where I have defined f of a to have. So you can see again, f of 0 is a required integral, right? Because when you put a equals to 0, this term becomes 1, and this is the required integral. But this is what we need. And f of infinity is simply 0. So we'll do that again here. We'll simply integrate both sides, f dash tail dA, and this should be, let's do it from 0 to infinity. Cot inverse A whole square dA. In a minute, we are going to change the name of the integration. A is not really suitable here. So, okay, 0 to infinity. We are doing from 0 to infinity, correct? So, again, due to fundamental theorem of calculus, this would be f of infinity, which we have discussed. Limit a tends to infinity, f of a should be 0. So, this is 0 minus f of 0. And this is simply minus 0 to infinity. Cot inverse a whole square dA. So you can cut off the minus sign, and what you get is f0 is a required integral. F0 is simply equals to 0 to infinity, and let's write it using x naught, cot inverse x whole square dx. Right. Now the next step, let x equals to cot y. This would give us, okay, so the derivative of cot y is minus cos x square, right? So it's minus cos x square y dy. So f0 basically becomes, now let's calculate the limits. So cot y is basically 1 upon tan y. So you can understand what's going to happen here. Basically, we are putting the value of x and we are trying to find the value of y, because it's useful to write that y is cot inverse x. So when x is 0, what is cot inverse 0? Cot inverse 0 is basically when the value you put. So if you do not know inverse trigonometric functions, this is a good place to learn actually right now, because otherwise we are not going to really understand everything that's going on here after this step. So this becomes basically pi by 2. Okay, so if you see that cot of pi by 2 is 0, that means cot inverse of 0 should be pi by 2. Similarly, cot inverse of infinity, so cot 0 goes to infinity. That is why this would be a 0. Okay, those are the limits. Then you have like y square, and then you have dx as minus cos x square y dy. Absorb the minus sign into the limits to get 0 to pi by 2 y square into cos x square y dy. Now, here is a function which can be integrated, which has an integral you already know, right? So this is begging to get integration by parts. So let's apply the first function as this one, second function as this one. Basically, this one is u, and this one is my dv. And when you do this, you get simply this y square, and the integration of cos x square y, as you know, is cot y from pi by 2 to 0 minus 0 to infinity, 0 to pi by 2. Y square when differentiated will give you a 2y, and then cos x square y on integration will give you a minus cot y. That minus here would become a plus, and this would become a y cot y dy. And this limit basically goes to 0. You can check this on your own, that when you apply pi by 2, this is simply 0, and when you go like apply 0, you have to do limit y tends to 0 on this. That becomes 0 using that Taylor expansion of cot y. Okay. So this becomes 2, 0 times 0 to pi by 2, y into cot y dy. And again, we are going to apply integration by parts because we can. Simply. Because cot y again has an integrand, and it's a standard integral. Cot y's integral is simply log sine y, log mod sine y. So let's do that 2 times. So again, we will have y log of sine y. This would be from pi by 2 above and 0 below, and then again minus 0 to pi by 2. Differentiation of y would be 1, and we would be simply left with log of sine y dy. You can check again that this goes to 0, and our final answer here should be minus 2, 0 to pi by 2 log of sine y dy. That is f of 0 here. Okay. Now, since this is f of 0, now let's write it like this again. Now, we are going to evaluate this integral. Let's call it j. J is mine 0 to pi by 2 log of sin x dx. And since this is here, now what we are going to do is we are simply going to use the property. I will state the property here. A to b f of x dx is simply equal to a to b f of a plus b minus x dx. So let's use this property and we'll get 0 to pi by 2 log of sine of pi by 2 minus x, which is simply cos x dx. Now, both of these are j's, right? Add these two copies of j's basically, and you will get a 2j on the left and 0 to pi by 2. And now you're adding two integrations with the same limit, so you can add the integrands inside. And due to property of law, okay, let's do it in two steps actually for understanding it better. Log sin x plus log of cos x dx. Okay, therefore, this would become 0 to pi by 2 log of sin x cos x due to the property of logs. For reference, the property is log of AB simply can be written as log A plus log B. Great. Again, recall the formula that sine 2x is 2 sin x cos x. So if you were to multiply 2 up and down inside the log, the 2 sin x cos x would simply give you a sine 2x divided by dx. And apply the formula of log again, which is, as you can guess, multiplication turns into addition, so division would turn into subtraction. This would give you log of sine 2x minus log of dx. And you can write this as two separate integrals, 0 to pi by 2 log of sine 2x dx minus pi by 2 log 2. Obviously, the base is e. If not mentioned, the base is always e in general in calculus problems. In algebra problems, it's usually can, but it's obviously better to mention the base whenever possible. Okay. So now we are left with this final piece of integral, which if we manage to solve this one, I think we're completely done. Okay. So this one can be done. We can first substitute y equals to 2x here, which would give us dx equals to dy by 2, right? This would give us, the limit should be from 0 to pi, right? So 0 to pi log of sine y, and there would be a half here, and there would be a dy here, minus pi by 2 log 2. Great. Now there's a tricky part here. You can either apply a property. I'm not going to apply a property. I'm rather going to show you how to do it. Break this integral into two different integrals from 0 to pi by 2 dy, and from pi by 2 to pi. The same integral, log of sine y dy minus pi upon 2 log 2. Okay. Therefore, we started with j, right? It's 2j. So 2j is equals to half. The first integral is I, as you can understand. This is directly I, because y does not matter, as I've already told before. The variable change in definite integration would not really matter. You can write any variable in place of any variable, a new variable basically. The area should remain the same. In the next one, here, apply z equals to y minus pi by 2. And doing this also gives you dz equals to dy, so we do not really have to take care of the differential element here. So, but the limits become 0 to pi by 2. And inside we have log of y becomes z plus pi by 2. So this becomes sine of z plus pi by 2. And this becomes dz. And then there was a minus pi by 2 log 2. So this becomes half I plus 0 to pi by 2. And sine of z plus pi by 2 is simply cos pi, cos z, because you can calculate it using sine of a plus b. This is log of cos of z dz. minus pi by 2 log 2. Now, this then becomes half r. Now, you can apply the formula as stated before of a to the f of x dx is equals to a to the f of a plus b minus x dx. And if you do that, this would simply become 0 to pi by 2 log of sine z. And we can do the change of variable again, or you can simply understand that that integral would simply be I. So what I want to tell is this integral is simply equals to log of sine z upon applying the transformation that I had mentioned before, pi by 2 log 2. And this is again I, right? So what do we, this is again J, sorry, when I want to marry, this is all of this is J, all of this is J. So this becomes half 2J minus pi by 2 log 2. Half 2J is simply J. So our equation simply becomes 2J equals to J minus pi by 2 log 2. And this is simple to solve. This basically means that J is minus pi by 2 log 2. Now we can go back here and we can see what our actual answer was. F0 was minus 2J, right? Okay, so F0 was basically minus 2J, which means minus 2 multiplied by minus pi by 2 log 2. Cancel off the minuses and the 2's, you will get your final answer, which is pi by 2. Let me write it for one last time here. 0 to infinity, 0 to infinity, sin x, sin y upon xy multiplied by x plus y dx dy equals to pi by. And this is our final answer. So, uh, as you can understand why I have stated that this is going to be a difficult integral, but on a scale of 1 to 10, even this is like 6 upon 10. Trust me, this is 6 upon 10. As far as I know, like this scale is based on the amount of harder integrals I have done before, solved myself or learned. So this would be a 6 by 10 amount. But okay, so this techniques are fairly simple, but there should be a flow to them. Like once you start doing the problem, they should come automatically. We should be searching for the solutions and the methods to go further. Like what is the area under the curve? Like area. This is basically what, right? What is the volume spanned by this curve z equals to sin x and y upon x y or x plus y? And you can generalize it as you want. So this is probably the hardest thing to go right to, as I have mentioned in the title. Anyway, so if you do like this video, please subscribe the channel and also like the video and let me know in the comment section how you enjoyed it. Thank you.